Last year, I got the slides a week ago. My contribution to the talk is to try to help figure out what's going on. This is 6 months, a very large number of experiments on this work. This really is Mitchell's results. Raman's well known to be a powerful tool. There has been work on Raman spectroscopy on palladium hydride. So let me begin to make Raman type measurement on a surface very simple. If the light comes in, it can scatter. It is possible for there to be a scattered signal where one phonon has been created. If the surface is hot or has excitation of some sort, it's possible to get a scattered signal that has the addition of one phonon's worth of energy. Okay, so I'm trying to get some intuition. We'll be showing some spectra shortly. If you have a weak incident beam and you have a cold surface, you can expect to see a Rayleigh scattered peak with no phonon exchange. If the incident beam is stronger and you have a cold sample, it is possible for you to make phonons, in which case there's a small part of your scattered beam that comes out at lower energy or longer wavelength. If you have a stronger incident beam in a hot sample, then you can get your phonon loss here. You can get your phonon gain here. Typically, both of these are small compared to the Rayleigh scattering peak, and typically the anti-Stokes line is smaller than the Stokes line. In some crazy universe where some of the ideas that I've been arguing about phonon laser actually came to be true. The question is, how would you know whether you were seeing it? Well, one way is that the anti-Stokes would become roughly equal to the strength of the Stokes, but perhaps much more importantly is that the amplitude of the Stokes in anti-Stokes line would get larger, and in some limit where you've made a phonon laser, maybe they would be equal. Or if things went even larger, you could steal some of the elastic Rayleigh scattering amplitude. So in the limit that you always either gain or lose one quantum, you might expect to see a double. Now, Mitchell was actually interested in doing experiments to have this be less an intellectual argument and be looking at data. So here's data from Sherman. This is the first Raman observation palladium hydride. Basically, this line corresponds to this point right here around 8 or 9 terahertz. The optical phonon modes are here. You can see them here in frequency. Here you can see them in the Raman spectrum. Below here, you get acoustical modes, and the response is very large. Here's Mitchell's setup. He has a strong laser at 532 nanometers. It's around 150 milliwatts. He has a weak laser at 635 nanometers, around 2 milliwatts. The idea of the weak laser is to give a calibration line in his spectrum. In his paper, he didn't say what kind of lasers these are. I think they're diode lasers. This may be the world's only diode Raman measurement. Targets are here. The beam comes back, hits a grating, goes to a detector. Here's a spectrum of the elastic scattered beam only from a surface with no Stokes or any Stokes line, no broadening, no anything. You see the lines very sharp. Here's the visible version of the spectrum. Here's some spectra from rhodamine B. So here's the 532, the Rayleigh line. Here's the Stokes line. Here's the calibration line, fluorescence, and you can see the pretty colors. So this is demonstrated as a system can actually detect some kind of Raman lines. Here's zirconium oxide, nano zirconium oxide, again, the calibration pulse. You see some features on the long wavelength side of the Rayleigh peak. If we look at published data for crystalline zirconium oxide, it's the top, and this is frequency in this direction, it's wavelength in this direction, so these are Stokes lines. This is around 5 terahertz, this is around 19 terahertz. If we look at the zirconium oxide, this is sort of around 5 terahertz, this is sort of around 19 terahertz, and he's got an intensity difference. If I recall, this was taken around 400 milliwatts, a little bit higher intensity. So here's a zirconium oxide with nano PD, nano palladium, and with no hydrogen loading. And what's interesting is we see a Stokes feature. And we recall that the acoustical modes for pure palladium, the compressional mode is a little bit above 6 terahertz, the transverse mode is a little bit above 4 terahertz. So combination of these things with nanostructure, this thing looks like a good candidate for the acoustical mode response from nano palladium. And that's interesting because it's suggesting that the palladium is giving a bigger signal than the zirconium. This is from palladium nickel, nano palladium, nano nickel, and zirconium oxide. This is the response around 5 terahertz from, presumably from the palladium. This is at a higher frequency, presumably from the nickel. And the picture is that maybe the palladium and the nickel is segregated in their nanoparticles. Okay, so this summarizes it. Basically, his diagnostic technique is sufficiently good that we're actually seeing some Stokes spectra. We recall that the nanner looks something like this. He's got nanomaterial, which is constructed of zirconium oxide with palladium, nano palladium inside. These things are similar to what's been talked about in many presentations previously, including Takahashi's. This is crammed into his nanner. It's overpressurized with deuterium. His loading is very high. He's not said publicly how he makes these things. We've discussed previously how he's able to get excess heat. He runs a current through the nanner. He gets a thermal response. Here's a control. Here's the excess power. This is the input power for the nanner. Input power, excess power for the resistor, and so forth. So he's demonstrated reproducible thermal response previously. Here's a spectrum from an unloaded nanner with no current and with no loading. We can see the Stokes feature from the palladium, similar to what we've seen before. Here's the spectrum from a loaded component, again with no current. We see the Stokes shifted peak, not quite as clear as we had before. We're not seeing much from the optical photon modes. Here's our calibration pulse. Here's what the spectrum looks like in excess heat mode. So what's happened is Mitchell's applied a current. He's got some thermometry in this experiment rather than calorimetry, and from his thermometry, he concludes that this nanner, during the time that this data was taken, was producing excess heat. He's got a Stokes line, and he's got an anti-Stokes line, and in previous spectra, we didn't see an anti-Stokes line, and when the current is on, we see the Stokes line. So the title of the presentation that Mitchell submitted is a correlation of the anti-Stokes line with gain, thermal gain in the nanner. Now, I'm looking at this and I'm thinking both of these lines are not bigger than the elastic thing. Is this consistent with photon gain or not? It remains to be clarified. The fact that the anti-Stokes peak here is big is striking, and it was striking last year, and is striking as I look at the data now. Here's a logarithmic plot of it. Here's the Stokes peak, here's the anti-Stokes peak. number of terahertz. This is 5 some terahertz on this side, this is 5 some terahertz on the other side. So here's what happens when you run in avalanche mode. So Mitchell found that if he goes higher voltage, puts higher voltage across, he runs with this series and he runs into an avalanche. So the current goes way up. So this current is more than an order of magnitude higher than what he has before. Typically he sees little in the way of excess power. You might think either that's because there is no excess power or because the input power is very much larger than it was before, so the ratio of excess power to input power is it's much less and harder to be sure of it. But here we're seeing Stokes peak and the anti-Stokes a little bit smaller. And so here's an example of the avalanche effect from one of his earlier experiments. Here's some data that he's shown previously where here's the avalanche showing up. So he's increasing the voltage. The delta T over P in is decreasing. He interprets this as being excess heat being present. Once the avalanche kicks in, then the ratio ends up being very similar to what he gets from a resistor. And so under these conditions, he would say there's no power gain. So here's overlay of things. Here's no current. Here's current in excess heat mode showing the anti-Stokes. Here's the avalanche mode. The anti-Stokes is, you can see, is basically not there. The Stokes line is showing some variability. Here's a linear version of different data set. So here's everything off. Here's on in conditions where he would expect and see some temperature change corresponding with excess heat mode, and then avalanche mode. While I was putting together these slides, it occurred to me that his data was showing a doublet, and that caught my attention. And I called up Mitchell. I said, Mitchell, tell me more about this doublet. And Mitchell said, well, I have to respond to the patent office. I'm too busy. So if you can strangle somebody over the phone. Okay, so we discussed this. I don't know if this is visible from my angle. I can hardly see it. There's a line that comes up. So this is the two-dimensional wavelength is this way, space is this way. So the beam comes in and it scatters from scatters in different directions depending on where it is. This is scattering from where the active part of the nanner is. This is scattering from other places. So there's no shift. When it shows up on my computer screen, it looks pretty convincing that one line's going one way, one line's going the other way, and there's something of a hole in the middle. Here's a transverse scan down here, so you can see this is the calibration laser, so it's the low intensity laser. This is one that you normally wouldn't expect to see Stokes or anti-Stokes from. As you go up, you can see, I guess, splitting, perhaps anti-Stokes. Here, at this point, you're seeing a doublet showing up. In this data, in this data set, I haven't measured it exactly, but my wild guess is that this would correspond to a phonon laser near 2 terahertz, if that's what it actually is. Okay, so conclusions. Raman spectroscopy is a very powerful tool. When he drives it in excess heat mode, he gets an anti-Stokes signal, which is significant. He's got evidence for doublets, and as we've argued, the doublet in the data set showing up is showing up in the avalanche mode. I've asked him if he's got evidence for anti-Stokes or doublets in the laser on mode, and he said, well, what happened last year when he was taking data is he saw many examples of the doublet, and he thought he was making a mistake, so he tended to discard and not consider that data. When I return, I am intending to have some very long and heart-to-heart talks with him about his data sets. Thank you.